Welcome to a massive open online course on basic principles and calculations in chemical engineering. In module 4, we are discussing something about state equation of ideal gas and based on that some calculations, some material balance we have covered. So, under this module 4 basic principles of compressible system, in this lecture we will try to describe more about that state equation, but in this case especially for non-ideal gas state equation and also based on their equations we will try to do some problems on further calculations. Now we will describe about that what are the different basic equations of state for non-ideal gas and also how that properties of that non-ideal gas will be changing and how we can solve the problems we will describe here in this lecture. Now as we know that of course real gas that will be regarded as non-ideal gas, and that many gases are assumed to behave actually ideally at room temperature and pressure that we know. However, at high pressure the gas properties that you might obtain using the ideal gas law, that would be at that wide variance with the experimental data. So, that means at high pressure and temperature we can say that we are not actually having that properties of ideal gas here. So, this gas will behaving at that particular conditions differently from that ideal gas. Here in this case of course the behavior will be changing in wide variance as per experimental data because here in this case the molecule of this this real gases, or you can say that non-ideal gases does not actually in that state where it will interact with each other and all real gases will be in that case non-ideal. So, in this case in reality the molecule of a gas does interact with each other and all real gases will be considered as non-ideal. Even though the ideal gas equation of state may be a very good approximation at low pressure and high temperature, at higher pressure and lower temperatures the impact of that intermolecular interactions on gas behavior increases there. What does it mean here? You will see that we have actually used one ideal gas equation to represent its ideal gas behavior, but in that same direction if we that consider ideal gas equation of state for this calculation of behavior of real gas, you will see there will be a some approximated that value you can get at low pressure and high pressure for that real gases, but at higher pressures you will not get the same value. There will be huge that differences for this real gases at higher pressure and also you can say that at low pressures, low temperatures. So, in that case the impact of that intermolecular interactions on the gas behavior that will be changed because of this higher pressure and lower temperature, and because of what we can say that this ideal gas equation cannot be approximately given the same value at higher pressure or lower pressure. So, in that case we need to calculate that pressure, volume and temperature properties on gases which are not actually ideal, that also to be considered in the same fashion of that ideal gas equation. So, before going to that we have to understand that where is the difference of that ideal and the non-ideal gases. You will see that ideal gases that it will not satisfy the laws of that ideal gas at all conditions of pressure and temperature, whereas that real gas will follow the gas laws at high temperature and low pressure. There will be a certain equations where that you can use this that real gas behavior by which you can that interpret that real gas behavior. and in ideal gases you will see that no intermolecular attraction force will be there, whereas in real gases that intermolecular attraction force will be there. And in ideal gases there is elastic collision of the particles whenever it will be moving in a particular temperature and pressure, whereas in real gases you will not get any elastic collision of the particles during its movement. In ideal gases you will see that it will not actually really exist in environment and is a hypothetical gas, whereas this real gas it is really exist in the environment, whereas this ideal gas you will see that occupy any volume, whereas real gas will occupy certain or definite volume. Ideal gas it will be independent, whereas real gas interacts with other, and this ideal gas obeys PV is equal to nRT, that ideal gas equation, whereas this real gas will follow some other that equations like van der Waal equations and other equations of state, and in general you can express that non-ideal equation in the fashion of that ideal equation as PV is equal to Z nRT. Here Z is called compressibility factor, whereas in the ideal gas equation you are not having that Z factor here, only PV is equal to nRT, but in this real gas we are introducing one that compressibility factor to express the general expression of the equation of state. Here see in this slide one graphical representation as given by Himmel Blau in his textbook, that how that that real gases are deviated from the ideal gas at high pressure. You will see that here this P V by N, that means P into specific volume, pressure into specific volume of real gas, and pressure into specific volume for ideal gas in the x in the y axis, whereas in the x axis it will be that pressure. So pressure at different pressure, how that that real gases properties of that product of pressure and specific volume is changing. So at see that at higher pressure you will see that this real gases that this factor will be higher than that ideal gases here. So interesting that in this suppose there is a point here, you will see that this point will be almost 1 point that 37 like this. So at this condition you will see that, and at higher pressure more than 500 that atmospheric pressure, you will see that this real gases behavior of this V will be that 1 point almost 37 times of that ideal gases. At a particular that this temperature is that around 200 degree Celsius for hydrogen gases. So similarly for other gases also you will see that this ideality, or you can say that how it will be deviated at this high pressure, and also real gases behavior how it will be magnified at this high pressure for different gases. So from this graph you can easily calculate what should be that factor here, real properties compared to that ideal properties. Now in general you will see that there are 4 methods of getting or predicting real gas properties are there. You can predict that real gas properties either by equation of state, or by compressibility chart, or by estimated properties, or by actual experimental data. So either of these 4 methods you can follow to predict or gauge, or you can say that estimate that non-ideal behavior of the gases or real gases behavior by this. So let us consider that generalized equation of state by which you can express that non-ideality behavior, or you can say that real gas equation for expressing its pressure and also volume at a particular temperature. So one common way is to modify that ideal gas law by inserting an some adjustable coefficient, that is called Z here. So this Z it is called that compressibility factor. Now, from that you know that ideal gas equation, that is PV is equal to only nRT. Here in the right hand side you will see that we are just multiplying one factor, that is Z. It is called adjustable factor, which will be actually giving the same fashion of ideal gas equation, and in this case this Z it is called compressibility factor, and this compressibility factor you will get from this real gas behavior, and based on which you can say what should be the that pressure and volume there based on this compressibility factor, and it will give you that corresponding value of PV data for this real gas. So, we are actually expressing in the same fashion of that ideal gas equation. Here PV is equal to RT, here we are just multiplying one factor Z here, so that will be PV is equal to Z nRT. Now, this factor actually compensates for the non-ideality of the gas, and it describes the deviation of a real gas from ideal gas behavior. And also you can say that this ideal gas law, whatever expressed by this compressibility factor, will give the generalized form of that equation of state. Now, based on this generalized form of this equation of state, you will see that there are several real gas equations that is developed by different investigators, different scientists, and they have suggested different equations for predicting the non-ideal behavior of the non-ideal gas or real gas. So, in that case this that compressibility factor, whatever it is considered in this real gas behavior, that should be actually expressed by that temperature and pressure at its critical condition. Now, in that case this almost all fluids you can say that will obey the same equation of state when their properties are written in reduced form. What is that reduced form? That means here if we consider that compressibility factor, this will be actually represented by Z by ZC. What is that? Z is that compressibility factor at a certain temperature and pressure, whereas ZC is nothing but that compressibility factor is at at critical condition. We will describe that what is that critical condition, that means where that you will see that the gas will not be actually will not be able to liquefied at higher pressure or that particular temperature. So, that point of that temperature and pressure will be regarded as critical point of that temperature and pressure. So, if you express this compressibility factor based on that critical condition, it will be denoted by ZC. So, Z by ZC it will be regarded as a reduced form of that compressibility factor. So, this reduced form of this compressibility factor will be a function of reduced form of temperature and reduced form of pressure like this. So, we can say that reduced form of that compressibility factor is a function of TR and PR. TR is reduced temperature and PR is reduced pressure, and this TR is defined as T by Tc, that means T at certain that is temperature, and Tc is the behavior at that critical temperature. Since here this ZC is nearly a constant for many organic species, it is actually about 0.27, just remember this, and the most often used form is then we can write here Z will be equal to function of TR into TR and PR. So, this is why we can say that this reduced form of this compressibility factor will be a function of reduced temperature and reduced pressure, and as the molar volume of in that case that gases, real gases will be converting into that or tends to 1 for that compressibility factor if it is going to 1 there. That means as the molar volume becomes large, we can say that Z will be tends to 1. So, compressibility factor is near about 1 means it will give you that large molar volume of that gas. So, here we told that critical temperature and pressure, what is that? So, gases can be converted to a liquids by compressing the gases at a suitable temperature. At high temperature liquefaction becomes difficult because higher and higher pressures are required to overcome the increased kinetic energy of the molecules. In fact, there is some temperature above which the gas can no longer be liquefied regardless of pressure. This temperature is called the critical temperature. We can say that the highest temperature at which the substance can exist as a liquid, it will be regarded as that critical temperature. Above the critical temperature, the molecules have too much kinetic energy for the intermolecular attractive forces to hold them together in a separate liquid phase. Instead, the substance forms a single phase that completely occupies the volume of the container. The substances with strong intermolecular forces that tend to form a liquid phase over a high large temperature range. In that case, this substance will also have a critical pressure, and it will be the minimum pressure that is required to liquefy it at the critical temperature. So, we can say that above this critical temperature, molecules have too much kinetic energy for the intermolecular attractive forces to hold them together in a separate liquid phase. And also substances with strong intermolecular forces will tend to form a liquid phase over a very large temperature range. Now, here in this figure it is given that critical temperature and pressure of some gases here given in this table. For ammonia, this critical temperature will be at 132.4, whereas critical pressure will be equal to 113.5. Similarly, for other gases, this critical temperature and critical pressures are given here. And here in this figure, you will see that if we represent this non-ideal behavior of this gas, you will see that beyond this critical point, at this temperature, this gaseous mixture will not actually be able to converting into that liquid form. So, at this critical temperature, even what is the corresponding critical pressure at this condition, you will see beyond this critical pressure and temperature, you will see that there will be no formation of liquid gases there. And beyond this, you will see that there will be a properties of that gases will be drastically changes. So, this ranges of that operating condition of temperature and pressure will be regarded as the supercritical condition, and the phase whatever will give you that behavior, it will be called as supercritical phase behavior. And you will see that this at a certain temperature, even at a low temperature, even low pressure, you will see that at a certain condition, you will see that some like water, it will give you that vapor, liquid and solid, that three phases at a particular point, that will be called as triple point. And these are called that equilibrium condition of its different phases. So, in this case, you will see substances by this profile, it will be representing as some equilibrium between that here solid and vapor, whereas this equilibrium profile will give you that that equilibrium between that liquid and vapor. And in this case, here this line will give you that equilibrium point of that solid and that liquid there. So, in this way you can say that at different pressure and temperature, that substances can be changed into its different form just by changing its temperature and pressure. So, at high pressure, that means beyond this critical condition, these gases will not be liquefied, whereas before this critical point, you can say that some substances you say that that gases will be regarded as vapor. Even at a particular temperature, from this you will see that and if you change the pressure, high pressure, you will see that that gas may be converting into a liquid phase. Again, for a fixed temperature, and if you change that pressure, even at this condition, you will see that this liquid also, it will be changing at a particular pressure if you change the temperature from that initial point here. So here in this way you can say that you can change the temperature and pressure, and accordingly you can get the different points in this region of that different phases. That means here that phase will be converted at that particular temperature and pressure. Now to represent that non-ideal gas behavior, according to that that concept of ideal gas equation. So we are considering here that non-ideal gas general form of equation of that, it will be PV is equal to Z RT. Here small v is nothing but that molar volume. Here this small v is nothing but capital V by N. Capital V is that volume of that gas, and N is number of moles. So small v, that is a specific volume in mole basis, that is called that molar volume. So this V by N is represented here small v. So we can write that from the equation of PV is equal to Z and RT, we can write here Z will be equal to your PV by RT. So this PV by RT or Z, that is compressibility factor, you can represent it as a function of a specific molar volume. So it can be represented by this 1 plus B by V plus C by V plus D by V, where this B, C, D are all coefficients. Those coefficients are called virial coefficients, and these virial coefficients actually depending on the temperature of that particular system. You will see that this C and D values are that relatively going to smaller compared to that this second that virial coefficients. So accordingly we can say that if we neglect this two terms of right hand side, so remaining portion is 1 plus B by V. So from this 1 plus B by V you can directly calculate what should be the compressibility factor Z. Now in this case this B can be estimated from the following that correlations given here. So this coefficients basically depends on critical temperature and critical pressure. So this B value can be expressed as B is equal to here RTC divided by PC into B0 plus that omega into B1. Whereas this that B0 is a constant, that also depending on that reduced temperature. This is the equation to represent this B0 here, and B1 also is one constant, that B1 is also is expressed by this correlation given here in the slides. Whereas that omega is called eccentric factor. This eccentric factor will describe later on also. This some another factor that also is that depending on that temperature critical temperature and pressure there. So if you know that this eccentric factor and also that critical temperature and pressure, you will be able to find out what would the B value there. And once you know that B value, then what should be the that compressibility factor you can calculate from this equation. Now here one compressibility chart is given. This is basically the compressibility factor is as a function of reduced pressure, it is given here. So this compressibility factor versus reduced pressure, it is made, it is also taken from Himmel law, that is from your textbook. So you can go through that. Here see that how that compressibility factor, it will be changing with that reduced molar volume of that particular gases, and also how it will be changing with that reduced temperature, and also how it will be changing with your reduced pressure there. So, at a particular reduced temperature, that means T by Tc, and also reduced molar volume, there if you know that, then you can easily calculate at a particular reduced pressure what should be the compressibility factor. Let us have this some gases here. Suppose this reduced volume, molar volume is that here this point, and also that reduced temperature is 1, then at this particular reduced pressure, what should be the compressibility factor? Here it will you can get it from this point. So, in this way you can read what should be the compressibility factor from this chart. Now, we told that there are several equation of state that is suggested by different investigators, different scientists, different academician. Also you can say that how that real gas behavior can be expressed based on their intermolecular force, even their molecular size. So, in this case van der Waal equation of state is one of the important equation of state for the real gases, by which you can calculate its pressure and also volume for that real gases at its particular temperature and pressure. So, in this case see here van der Waal equation is given in the slide. Here it is P plus A into N square divided by V square into V minus NB, that will be equal to nRT. Here also P into V, here this part is regarded as P real, that is P plus A N square by V square. Here A is some coefficient, it is actually depending on the critical temperature and pressure, and its value is given here by this correlation. And here V real, that is denoted by V minus NB. Here B is also coefficient, this B is calculated by this equation. Here also it is depending on the critical temperature and pressure. You will see that two coefficients are here A and B. This A actually is a correction factor, that is accounting intermolecular force of that real gases, whereas B is another factor that accounts the molecular size of that particular gases. So, based on which that van der Waal suggested this equation of state to represent the non-ideal behavior of the gases. So, here in this case, if you know the measured pressure and also measured volume, you can easily calculate what should be the remaining factor of that A and B there, just by that equating that experimental data with this equation. So, one way you can express that what should be the A value and B value, that A and B value you can express by this that critical temperature and pressure. Also, if you know that measured volume at a certain temperature for that real gases, and also if you know that A and B value of that coefficient at this particular critical reduced temperature or reduced pressure, or you can say that critical temperature and pressure, then you can easily calculate what should be the pressure of that real gases. Whereas we have calculated the behavior of ideal gases only by PV is equal to nRT. Here in this case that will not give you the exact result for that real gases. So, that is why for real gases you have to use this van der Waal equations, because that real gases behavior will be different from that ideal gases, because of that some intermolecular force and also size of that real gases will matter. So, that is why based on that intermolecular behavior, that van der Waals given this equation of van der Waal equations to represent that non-ideal behavior of the gases. Similarly, another investigator, that is called Redlich-Kwong equation of state, by which you can express that real gases behavior for the pressure and volume. So, here also this equation given, this is also you will see that at this equation here you will see the molar volume of that real gases, and also some coefficient here B is given here. So, based on this you can calculate what should be the pressure if you know that molar volume is there. So, this again that this Redlich-Kong equation, depending on these two parameter, this A and B, those are actually depending on that intermolecular force and intermolecular that or molecular size there, and these coefficients are again depending on that critical temperature and pressure, and by this correlation you can directly calculate or estimate the value of A and B. Once you know that A and B by these correlations, and if you know that molar volume at a particular temperature, then you can easily calculate what would be the pressure of this that real gases by this Redlich-Kong equation. Similarly, other equations are also familiar to calculate or predict that real gases pressure or volume. So those are Peng-Robinson equation of state here given. Here again some factors are here, some A and alpha, even that B, even you can say that this alpha value, that is eccentric factor, also this alpha value depending on that some that eccentric factor. In that case you will see that some other factors, it is denoted, that is called K, that is also depending on the eccentric factor, and also we can say that this coefficient A and B are depending on that critical temperature and pressure, and Vm is here molar volume. So based on this equation also you can calculate what should be the pressure. Similarly, you can use that SRK equation, it is called Swab-Redlich-Kong equation. Here also this equation expressed in terms of some coefficient B and also here alpha and A. Here A is defined by this correlation, B is defined by this correlation, alpha is again depending on that eccentric factor and the reduced temperature, and this reduced temperature is defined as here T and Tc, and this alpha is equal to here 1 plus m into 1 minus root over Tr whole square. This m is basically that as a function of eccentric factor, and R is that ideal gas constant or universal gas constant, that is 0.08205 at this unit of liter atmosphere per mole Kelvin. So from these equations you can easily calculate what should be the pressure and volume at a particular temperature there. Now constants for the van der Waals and Redlich-Kong equations are given here in this table for different gases, that means A value, B value, what should be that. So from this table you can take this A and B value directly without that calculating that A and B constants from the correlations. So you can directly use this table for your A and B, and after getting A and B, if you directly put that that A and B in your respective van der Waals equation or Redlich-Kong equation, then you can easily calculate what should be the pressure or volume. Now let us do an example based on this that van der Waals equation or other equation of state. Now as an example you can say that if suppose a cylinder of 0.15 meter cube, here 0.15 meter cube in volume containing 22.75 kg of real gas A stands in the hot sun. Now a pressure gauge shows that the pressure is 4790 kilopascal, that is in gauge. What is the temperature of the gas in the cylinder that you have to find out. Now in this case you can use the van der Waals equations, because here this gas is real gas, so you cannot use that ideal gas equation to find out that here temperature. So in this case if we use that van der Waals equations, for that what we should require to calculate. In this case this is your van der Waals equations. For this you need to calculate A value, you need to calculate B value. So A value can be calculated based on that correlation. So you can get directly this equation, or either you can take it from the tables. So this A value will be like this, and B value will be equal to similarly 90.7, or you can calculate it from the correlations that is given. in the earlier slides. And once you know this A and B value, then you have to calculate what will the N value there, because N is also to be calculated. What will the number of moles of that gas is, because in this case it is given that cylinder contains 22.75 kg of real gas. In this case, if real gas here molecular weight is 44, let it be here. So in this case the number of moles will be is equal to here 0.517 kilomole, and pressure is given there. I think what is the pressure is given, it is you know that 4790 kilopascal. So here it will be you know that absolute pressure will be equal to, this is gas pressure, so absolute pressure will be equal to 4790 plus 101, this is your you know atmospheric pressure. So you have to add it up to get the absolute pressure, and this is in kilopascal. You know that 101.3 kilopascal is equivalent to 1 atmosphere. So you can convert it to absolute pressure into atmosphere. This is 48.3 atmosphere. Then and R value is as per that atmosphere, it is you know that 82.06 centimeter cube into atmosphere per mole K. You can say that after substitution of this you know that N value, A value, B value, and also volume is given to you, it is given 0.150 meter cube. So you have to convert it to centimeter cubes, and then finally you can you know calculate that what should be the you know temperature from this equation. So this is coming, this will be equals to 384 Kelvin after substitution of all these parameters there. So finally we can say that the gas in the cylinder will have this temperature of 384 K. Another example, in this case you have to determine the hydrogen pressure in a tank by using you know SRK equation, that is Swab-Redlich-Kong equation. The tank is at 40 degrees Celsius, it is there. The molar volume of the hydrogen is 0.3 liter per mole. Now critical temperature and pressure of the hydrogen are given as 33 K and 12.9 atmosphere respectively. Now hydrogen eccentric you know that factor is given as minus 0.216. So what should be the you know the hydrogen pressure in the tank. So you can use this equation, SRK equation. Based on that you are having this P is equal to RT by B minus V minus B minus alpha A by V into V plus B. So in this case you need to calculate first what should be the A value there by this correlation. In this case, since this correlation or this value of A is depending on critical temperature and pressure, this critical temperature and pressure of hydrogen is given to you. So finally you can calculate what should be the A value. Similarly, what should be the B value, again if you substitute the TC and PC, there you will get this value 0.018, and then you have to calculate what should be the you know M value there, because to calculate that alpha value it is required that M value. So M value is a function of eccentric factor, this eccentric factor is given to you. So if you substitute that eccentric factor omega here in this equation, you can calculate what should be the M value here. So M is coming as 0.143. Then finally you can get what should be the alpha value here. Before calculating this alpha value, you have to calculate what would be the reduced temperature, because this reduced temperature is defined as T by Tc, T is given to you and then Tc is also given to you. So finally you are getting that 9.49 as Tr, and then what should the alpha value after substituting of this M value and Tr value, you can get this alpha as 0.495. Now if you substitute that alpha value, A value, B value and also molar volume here in this equation at that particular temperature, what should be the you know pressure, you can easily calculate there by this SRK equation, and it is finally coming as 89.8 atmosphere. So this is your basic equation how to calculate the pressure and volume by this SRK equation. Another important you know aspect of non-ideal gas behavior is whenever there are more than one real gas will be there in a mixer, how then that you know they are you know reduced temperature and reduced pressure will be changing. So, in that case that also to be calculated, and accordingly that that compressibility factor of that mixture of gases will be will be different. So, once you know that mixture of gases, that compressibility factor, then what should be the pressure and volume from that non-ideal behavior or non-ideal gas equation, you can calculate those pressure and volume. Now, if you have that mixture of gases, then your critical temperature and critical pressure will be represented by pseudo reduced quantities of that gases to assess the pseudo critical properties. Now, it is used in generalized compressibility charts. So, according to the rule of Kay's, it is called Kay's mixing rule. So, this critical pseudo critical temperature will be regarded as what is the summation of yi into Tci. I is for individual component of that gases. Suppose there are 2-3 gases in a mixture. So, each gas components will be represented by I, and its molar fraction will be equal to yi, and Tci is the individual gas components critical temperature. So, summation of all this yi into Tci will give you that critical pseudo critical temperature of that mixture of gases, and also what is that pseudo critical pressure of the mixture of the gases. Similarly, you can have the summation of yi into Pci. But in this case you have to remember that sometimes this hydrogen and helium gas does not follow this that particular this critical temperature of this pseudo critical temperature and pseudo critical pressure just by that that individual gas component its that critical temperature and pressure. It is seen that this critical at this critical condition, this hydrogen and helium gases will give you the pseudo critical condition if you add it some factor there with that critical temperature. Similarly, if you add some factor of that critical add some factor with that critical pressure, you will see that pseudo critical temperature and pressure will be there. So, remember that for only hydrogen and helium, this pseudo critical temperature will be equal to Tc plus 8K. Here only this value of 8 it will be added to this critical temperature. Similarly, for pressure also you have to add this 8 for the critical pressure to get its CO2 critical constants here Pc dashed. So, this that for hydrogen and helium that you have to remember this equation to calculate further. Now, the pseudo reduced pressure and the pseudo reduced temperature are calculated using by this equation here. Tr dash it will be T divided by Tc dash, Pr dash it will be equal to T by Pc P by Pc dash here, sorry, P by Pc dash. The equation of state for a non-ideal mixture is then defined as PV will be equal to Zm RT. What is Zm? Zm is the compressibility factor of the non-ideal gas mixture. So, M is for mixture. Now, compressibility factor of the mixture, then you can calculate in this way. This Zm will be equal to Z0 plus omega into Z1, where Z0 is defined as 1 plus B0 into PR by TR, where B0 is defined by this correlation which is a function of reduced temperature, and Z1 is another factor that is that is a function of ratio of reduced pressure and reduced temperature, whereas this B1 is that coefficient is a function of reduced temperature which can be calculated from this correlation. So, once you know this this Z0 by this equation and Z1 from this equation, and if you know the eccentric factor, then you can easily calculate what should be the mixture compressibility factor. Let us do an example here. Suppose a gas mixture is given to you and that will contains 30% carbon dioxide and 70% ammonia. and it is exist at 500 Kelvin and 120 atmosphere in a container. The molecular weight, critical temperature and pressure for that carbon dioxide and ammonia are given here, and also the molecular weight, critical temperature and pressure for the ammonia also given. Find the molar volume of the gas mixture using that case mixing rule. Here eccentric factors of the carbon dioxide and ammonia are given as 0.228 and 0.53 respectively. So, you have to find out here what should be the molar volume of the gas mixture. So, to find out here what should be the first, calculate what will be the TCM for that mixture. For that mixture TC, since here fractions is molar fraction is 30% and 70%, then you just simply multiply that molar fraction as here 0.3 into 304 plus 0.7 into 405.4. Here 304 is the that it is given that critical temperature of the carbon dioxide, and 405 is the critical temperature of the ammonia gas, and their corresponding mole fraction for carbon dioxide is 30%, whereas that ammonia gas is 70%. So, total mixture critical temperature will be just based on this equation, it will be coming as 374.98 Kelvin. Similarly, critical pressure of the mixture, simply you have to multiply with that mole fraction and then add it up for all components, and it will be coming as 101.59 atmosphere. Here eccentric factor also you have to calculate in the same way of what is the mole fraction, you have to multiply that eccentric factor with that respective mole fraction and then add it up for all the gas components, then you will get this that eccentric factor of here as per problem, here it is 0.2455. Similarly, mixture molecular weight to be calculated based on that molar concentration here, so it will be as 25.10. Next, you have to calculate what should be the reduced temperature. It is defined as simply T by TCM. T is the temperature at a certain condition it is kept. This is I think 500 K, and TCM it is calculated earlier, that is it is coming 374.98. If you divide it this 500 by 374.98, you will get this 1.333. It is simply reduced temperature. Similarly, you can get the reduced pressure as 1.181. So, in this way you can calculate what will be the reduced temperature and reduced pressure. After that, you have to calculate that all coefficients given here like B0 and then B1. That TR, that means reduced temperature and reduced that pressure if it is required. I think only this in this equation only reduced temperature is required. So, B0 will be equal to this. Similarly, B1 it is also function of only reduced temperature. So, you can calculate this value based on that reduced temperature. Now, Z0 is a function of reduced pressure and reduced temperature. If you substitute this value of B0 and this PR and TR here, you can simply get this value of Z0 as 0.82 M. And similarly, you need to calculate that Z 1, this what is that, this is B1 into PR by TR, PR and TR here, and B1 already you have calculated. So, if you substitute those B1 and PR and TR here, you can get this Z1 value. Now, since this mixer compressibility factor is a function of this Z0 and the Z1, then you can have this mixer compressibility factor after substitution of this value of Z0 here whatever you have calculated and Z1 whatever you have calculated, but eccentric factor of that mixer also you have calculated here, it is given. So, after that simplification, you can get this that's value of 0.845. So, this is your compressibility factor of the mixer. Then what should be the molar volume of the gas mixer, that can be obtained from this that non-ideal gas equation, that is general form of that non-ideal gas equation, that will be equal to V, that will be equal to Zm RT by P. So, here Zm already you have calculated, and then R is given there, and T is 500, and what is that, P is here 120 K. So, finally, you can get it what will be the value, it is 0.289 liter per mole. So, in this way how this case rule of mixing you can apply for that mixture of non ideal gas to calculate its mixture molar volume. So, you have to follow this equation. Another example, suppose that a container or you can say the tank contains 3.5 kg of liquid oxygen which is to be vaporized in that tank of 0.0284 meter cube here, and that this will be vaporized at this at above this temperature of minus 25 degrees Celsius. Now, what will be the pressure in the tank will be, and will it exceed that safety limit of the tank, what is actually to be maintained at 100 atmosphere. In this case, given that critical temperature of that gases is 154.4 Kelvin, and critical pressure of that gas here oxygen is given 49.7 atmosphere, and reduced pressure is here 1.43. So, based on this condition you have to find out what will be the pressure inside the tank. Now, here in this case we do not know the pressure of the oxygen in the tank. Now, we need to use the other parameter like here VRI, that means for a particular component what should be its that reduced molar volume. So, to calculate that first of all you have to calculate molar volume of that gases. So, molar volume it is coming that its volume is given is that 0.0284 of that container, and its that mass of that gas is given 3.5 kg. So, meter cube per kg it will be 0.0284 by 3.5, and if you convert it to this meter cube into that again into mole, what is that you can get it to the mole just by that multiplying it with this molecular weight. So, in this way you can calculate that this will be your that this meter cube per kilo mole. So, this tank will be having this that volume of 0.260 meter cube per kilo mole of that oxygen. Now, what will be the VCI critical molar volume of that component? So, it will be RTC by PC. So, accordingly if you substitute that R value, TC value and PC value, you can get it this 0.255 meter cube per kilomole. And again this what will be the reduced molar volume of that component? It will be simply that V by VCI. V is already you have calculated, and VCI also you have calculated. If you divide this you will get that 1.02. And what will be the reduced temperature? This is T by TC. If you substitute that T value and then substitute the TC, you can get this TR value. And then what should be the PR? PR will be equal to 1.43, it is given to you. Then P will be equal to what? P will be equal to PR into PC. PR is given to you, PC also to be calculated, and then PC is coming here, it is also given 49.7, and then it will be coming as 71.1 atmosphere. So, at this condition the pressure of tank is 71.1 atmosphere, whereas at its safety level the pressure will be maintained as 100 atmosphere, but it is coming here 71.1. So, we can say that it is in safe condition. So, in this way you can calculate based on that critical temperature and pressure, and how to calculate that molar volume, and also at critical condition how to calculate the molar volume of each component in a particular tank, and also what should be the reduced molar volume for that particular components in the tank, and based on which you can easily calculate what should be the this that pressure simply from this reduced pressure and critical pressure there. So, we have discussed then a lot of that theories how to calculate the the pressure and volume of non-ideal gases based on that van der Waals equation, even our RK equation, even you can say that SRK equation, even other equations also are shown there to calculate that non-ideal behavior at a different temperature, even at different pressure and volume, what should be the other specific property of the gases, and also in a mixer how to calculate that compressibility factor by K's rule that we have discussed here. So, I think you have understood this matter how to calculate that non-ideal behavior by this equation of state if you know the compressibility factor. So, I would suggest you to go this textbook thoroughly, and also try to practice some other example problems given in the textbook, so that you can easily understand. Also you can further solve the problem based on this concept there. So, I thank you a lot for your kind attention here, and next lecture we will try to discuss more about gas system or that other system. In that case the separate module will be considered. In the separate module we will discuss something more that multi-phase systems, and their how they are actually lies in an equilibrium condition, and what are the different laws to express that equilibrium condition we will be discussing in the next lecture. So, thank you.